Now, what is going on, everyone? Today we are going to talk about JSON Web Tokens. And one more thing before we get started, since this video is probably going to be a little bit longer, I will put timestamps in the description down below. So in case you're bored or you already know like what we're talking about and you're only interested in specific topics, you can just jump ahead. And another note here, so I'm just doing like this video to prepare for an upcoming series. So what we're going to build is we're going to build a server-to-server communication based on JSON Web Tokens. And in order to build a JSON Web Token communication, we first need to understand what JSON Web Tokens are, right? And that is pretty much what we are going to do in this video. So I would say let's immediately get started. So if you look at the RSA 7519 specification, then you will find something like JSON Web Token is a compact URL-safe means of representing claims to be transferred between two parties. Yeah, so that is kind of like a little bit abstract. So maybe we can express this like in a simpler way, right? So what we can say is that JSON Web Tokens is a standard for transferring data that can be signed or encrypted. And that is really important. So the last part here, right? So it can be signed or encrypted. I think the encrypted part should be fairly clear, right? You write a love letter. You don't want everyone to know it, to read it. So that's why you encrypt it, so no one can read it, okay? But I just specifically wanted to dive into signatures because maybe that might not be so clear or not so intuitive. And yeah, let's just have a look what signatures are. So the purpose of signatures is that we are able to be sure that the data we have transferred is not modified. So let's make like a concrete example here. So let's say we have Alice and Alice wants to send some data over to Bob. So in that case, this would just be like a JSON object with like some CTA subscribe, which is a very subtle hint actually for subscribing to my channel. Just wanted to say that. I just had to bring that. So yeah, I mean, we want to send over this to, want to send this over to Bob, but we don't know what's happening here in between. So this could be like the internet, but it could also be like, you know, other persons doing crazy things with this object, saving it to a file, uploading it to some other components, importing it into, I don't know, whatever. So we want to be sure that Bob receives the exact same message, like every single bit that Alice created, and nothing less and nothing more. So basically we want to receive this thing as is. And at the moment we can't do this, right? Because it just could be modified like along the way, and we have no way of detecting that it was modified. And this is exactly where signatures come in. So signatures allow us to be sure that the data has not been tampered with, so that the data wasn't modified, and implicitly you also know that it comes from a trusted source if you can verify the signature. And the way this works is, instead of just sending like the plain payload or the plain object, what Alice is going to do is she's going to create a signature. And this concept of like digital signatures might be a little bit weird and unintuitive, right? And also, why is there like a header here? So let's maybe explain this from the very start. So if you have a signature like in the real world, right? Say a rental contract. Then what you do is you always put your name underneath, right? So you always sign with the same name, hopefully. And so basically the name you put under your rental contract would be the same that you would put under your phone contract. And that is where digital signatures differ. So what digital signatures do is the signature that is going to, or that we produce is different depending on what content we are signing. So the signature takes the actual content into account. And there's also like a second component to it. So it's not that we just take the content and do something with it and hash it or whatever, but there's like a second piece, which is typically like some secret or some private key that you never ever share. And this private key is like taken into account by some signature algorithm. So the common one that are used in JSON Web Tokens are like HS256 and RS256. We're going to cover them in a second. And basically you have this private key, and this generates like the private key and the content are basically used as input into the signature algorithm, which will then create the actual signature. And I just wanted to say this is like one way. So you cannot easily go back from the signature to the private key. It's like computationally infeasible. So we have to be careful here. Like technically speaking, it's not impossible. If you could brute force just anything, but it would take you millions or billions of years. So that's why I said it's totally infeasible to do so. Okay, and that is basically the difference between like a signature, like you know it from a real world, and a digital signature. So it takes into account the content, and you have like some private key. So this is typically something that you just generate up front. And in this scenario that we have described above, if Bob wants to be sure that the data he's receiving is the exact same or is like created by Alice, then they must have exchanged some form of key or secret before. And that means if this data finally ends up at Bob, what he's going to do is he's going to say, oh yeah, I know like the signature, or I know I have like this key or this secret to verify the signature. And I'm just going to do that. And if it fails, then I know that this is not the original data that Alice sent. And if it succeeds, then I know that this was signed by Alice, because no one else can basically create this signature. So this signature, this blue thing, is basically unfakeable unless like you have this private key or like this secret. And there's different ways on how you can create signatures, but we're going to go into detail for that in a second. And I just wanted to mention one more thing. So you just saw, okay, I'm somehow taking some content. So for example, subscribe to my channel, and I am generating a signature. So why do I have this header? So I just put this header here because in JSON Web Tokens or with JSON Web Signatures, you have like a header that contains metadata. And inside of this header, for example, you specify which algorithm you have used to generate this signature. So I just put it here as for the sake of completeness, but we will go into detail for that as well, like what different types of signatures there are, and shared secret and private and public keys and all that kind of stuff. But the important thing to understand is if you have a signature, it takes some content into, like you have some content, and you have some secret or private key, and you put this thing into the signature algorithm, and then it's going to output the signature. And the other party can then verify the signature. It can say, yes, this thing was created by like Alice in that case, because that's just how the signature algorithm is designed. Cool. So that is pretty much signatures. Like, let me know if you have any questions in the comment about that. I think encryption should be fairly clear. And now we actually already come to the gist of JSON Web Tokens. So if we talk about JSON Web Tokens, like in its pure form, basically you have two different types. And that was already mentioned in the beginning, where I said, okay, a JSON Web Token can be either signed or encrypted. So in its pure standalone form, basically, a JSON Web Token can either be a JSON Web Signature token. So this is the thing we just talked about. You have some payload, you sign this payload, and then afterwards, the second person or the second party can verify that this payload was not modified. And one more important thing to note here is that this signature process does not mean that your data is encrypted. So it only means that if someone attempts to modify it, you will know. But it still means that everyone can read it. And that is basically the distinction between JSON Web Signatures and JSON Web Encryption. So if you're talking about JSON Web Tokens in general, then you have two different types. The signature-based tokens, and the encryption-based tokens, and they provide different guarantees. So as I just said before, you have the proper keys, you know if someone modified the content because you can verify the signature, but the data is not encrypted. And with encryption, and that is like what we just briefly went over, with encryption, you can make sure that like only the person with the proper key or with the proper secret can read your data, right? It's like a ciphertext. It just looks like garbage if you look at it, and there's like pretty much no way you can recover the original text unless you have like some secret or some private key. And another way to look at this, and I think this is extremely important to understand, if you look at it from an object-oriented programming perspective, you can say JSON Web Token is kind of like the abstract base class, and then you have two concrete types. So you can either have like a token with a signature, or you can have a token with encryption. And most of the time, if people talk about JSON Web Tokens, they are talking about JSON Web Signature tokens. So people are a little bit sloppy. So if they were accurate, they would actually say, yeah, I use like JSON Web Signature, but people just in general say JSON Web Token. And some of you guys might now think, well, the signature thing is kind of nice, but kind of this encryption just sounds better, right? And I just wanted to mention this right here. So signatures and encryption, they provide different guarantees. So it's not that one type of token is better than the other type of token, but actually they work really well together. And we're going to see what you can do with that in a second. Like you can also use these tokens together and nest them in one another. And we're going to cover in this video like what you can do with it. Yeah, so that is pretty much the important thing I want you to understand. Someone talks about JSON Web Tokens. Most of the time people are talking about these signature-based tokens. But if they were really accurate, they would actually talk about, they would say JSON Web Signature or JSON Web Encryption. And as part of this video, we're mostly going to cover like JSON Web Signature because it's so common. JSON Web Encryption is like more technical and goes like into the very details of encryption and symmetric and asymmetric ciphers and that kind of stuff. So yeah, maybe that's like part of another video if you guys are interested. So let me just know in the comments down below. Cool. So let's just move on with this. And now you might have asked yourself, well, what are these things useful, or like what can I do with these things? So for one, JSON Web Tokens, specifically JSON Web Signature tokens, are very good for server-to-server communication. So for example, if one team operates like server A and another one operates server B, what you can just do is, instead of using something like HTTP basic auth, you can just say, okay, I'm going to create a token. And previously we have exchanged like keys or secrets. And then I'm going to send you a request. And server B is going to check like the token that server A has sent. And then it's going to verify this token and it's going to say, yep, that message comes from server A, or no, that token is invalid, or it doesn't, the signature is invalid from that token. And that's why this token is not coming from server A. That's why I don't trust it. And that's why I'm just going to ignore it or return an error. Another use case that you will quite often see is something called client-side sessions. Now, client-side sessions do have like a couple of security implications. So it's not that, you know, client-side sessions with JSON Web Signature tokens like the best thing that was ever invented. It does have security implications, and you just need to consider that. But I think this is also like a topic for another video. But I just wanted to explain like the concept in general. So normally, if you're talking about sessions, the way this works is you have like a browser, you log someone in, you send like the credentials to the server. The server is going to compare like the password hashes. And if they match, the server is going to create a session. And this session is then stored inside of a session store. So basically we now have a stateful solution. And this session is going to be associated with a specific session ID. And this session ID is put inside of a cookie and is sent back to the browser. And for every follow-up request, the browser is going to send the cookie along. And if you make a follow-up request, the server is going to fish the session out of the session store, and it's just then going to use that the session. And what like a typical values that you would store inside of a session would be your preferred language, your roles, maybe like some kind of user ID or client ID, something that uniquely identifies you as a user. And now some people say, yeah, but that requires me to kind of maintain this session store and I don't want to do it. And yes, that's totally true. So what you can instead do is what I just labeled as client-side sessions. So instead of storing this instead of storing data like in a session store, you can say, okay, I'm going to log in, and this server is going to say, yeah, if your login credentials are valid, I am instead of storing like a session inside of a session store, I'm just going to create like a JSON Web Signature token. And since we have just learned that you cannot modify this token, that you can only read it, I can just send this thing back to you. So for example, in a cookie, and then you're just going to send this cookie along for every single follow-up request. And since only the server has like the secret or like the private key to create these kind of tokens, you can be sure that no one can mess with this token, right? So if you have like a specific role, I don't know, say if you only had user, like you can be sure that people just cannot upgrade like their role to admin, simply because then the signature would no longer be valid and we would immediately know that someone has tampered with the data, right? Okay, cool. So that's like one other use case. And another use case that you will see quite often for JSON Web Tokens is that you can use them as bearer tokens for OAuth 2. So I'm pretty sure that you have probably seen these buttons like login with Facebook, login with Google, login with Apple. That's kind of new. And here oftentimes or sometimes JSON Web Tokens are used as bearer tokens. So that means a third-party application like with OAuth can access parts of the data of your Facebook account or Google account, for example, and you don't need to share like passwords. And JSON Web Tokens can be used as bearer tokens for these kind of applications. And there's also OpenID Connect, which is kind of like a little bit different. So it kind of builds on OAuth 2, but that's also like a different story. So basically for these type of use cases, OAuth 2, OpenID Connect, federated identity, single sign-on, that kind of stuff, these tokens are also frequently used. And now we have covered pretty much 3 use cases for JSON Web Signatures, but I also wanted to cover one for JSON Web Encryption. And that one is interesting because I just wanted to show you how in principle you would be able to implement a end-to-end encryption. So let's say you have some data that that is pretty sensitive. So for example, like an IBAN, like banking data, financial data. And you say, yeah, I mean, HTTPS is kind of fine. I kind of trust TLS. But sometimes, you know, people don't upgrade in time. This thing can have bugs and it's just not safe enough for me. Because if this data is leaked or someone manages to break into it, then I can pretty much close down my business. So this is the case like for banks or for companies dealing with health data. And in that case, what you can do is you can combine JSON Web Signature and JSON Web Encryption. And that's actually pretty interesting because you take the payload and what you do is you sign this payload. So now you get you have this payload, you have a signature and a header. Like that's what we just learned. That's how a JSON Web Signature token looks, like these 3 parts. And then you can do some kind of inception type of thing. You can basically say, okay, I'm just going to create a token inside of a token. It's like a matryoshka doll, like a puppet inside of a puppet, right? So you take this thing and you put it as a payload of an encrypted, of like a JSON Web Encryption token, right? So if we scroll up real quick, just wanted to show you. Yeah. So basically what you do is this ciphertext here is going to be a JSON Web Signature token, just encrypted. So you have a token inside of a token, which is a pretty interesting approach, because now you get basically both, or the best of both worlds, right? You know that this data wasn't modified and no one can read it. So this approach is pretty interesting. So you have a JSON Web Encryption token, and inside of it you have a JSON Web Signature token. And then what you do is, before you send the request, now you use HTTPS or TLS. So that means your TLS, like your transport layer security protocol, is going to encrypt your payload or your request. But the payload itself is already encrypted because it's a JSON Web Encryption token. And inside of this encrypted token, you have a signed token. And now you can see you have like a crazy level of security now, because even if someone somehow manages to, I don't know, break TLS, or I don't know, use some exploit, maybe because you haven't updated like your certificates or like your TLS version in time, the data that this person is going to get is like totally useless. It's like garbage, because the payload itself is again encrypted, and only the party, or like the person who has the proper keys or the proper secrets, can actually decrypt this. And this is how you would implement JSON Web Encryption. Okay, so these are a couple of use cases, and I would now like to go a little bit into detail on like how these signatures work, these JSON Web signatures, because that's what we want to focus on. So you previously already saw like this weird setup, right? You have a header. This was the thing I always drew in red. Then you have like a claim set and a digital signature. So that is basically the building blocks of a JSON Web Signature token. So all JSON Web Signature tokens consist of these three things. Now I do have to mention there's also tokens that don't have a signature, which kind of defeats having the purpose of JSON Web Signature tokens in the first place, right? Because if you have no signature, why would you even bother with this, right? Okay, so let's go through the individual parts. So the first part, this red part here, is called the header, and sometimes it's also called JOSE. I don't know if it's called JOSE, or I mean this JOSE stands for JSON Object Signing and Encryption Group. So it's basically the committee that came up with all of this, and it contains metadata, and it contains metadata primarily like about the signature itself. And there's like one field, so to say, which is mandatory, and this is this ALK field. And this ALK field indicates what algorithm you have used to create the signature. Because some of you might say, oh well, but I mean, I can just, if I want to sign something, I can just, send the stuff in my own format. Or if I want to encrypt something, why do I need this 5-part structure of JSON Web Encryption? I can just take the payload and encrypt it. And there's actually reasons for that, because you want to know, because it's just easier, right? If you have this thing, you just don't know, like if you have this garbage, this signature, or like this JSON Web Encryption token, you just don't know like what algorithm was used to create this signature. And maybe you have like different algorithms for different endpoints, or you have different keys, because most probably you will have some key rotation mechanism. So like every year you kind of change your key, or I don't know, every quarter, or whatever your security policy is. So every quarter you change like your key, and now you have like some token, and all of a sudden you don't know which key was used to encrypt this, and now you can no longer read it. So it definitely makes sense to have like a more structured approach, both for JSON Web Encryption and for JSON Web signature. And that is why you have this header part basically of the JSON Web Token. It makes like a lot of sense, and there's like more to it. So you can have there's like way more key value pairs, also a lot of predefined key value pairs. But I find that the two most important things are key ID, which is the ID of the key which you use to sign it. Like obviously not the key itself, but like just some identifier for the key. So if you have multiple keys in use, you know what key you use to create this token. And then also the algorithm. This one is important for verification. Okay. And then you have like the claim set. Now claim set sounds like a little bit complicated, but what it actually means is it is just a payload. So what you know as a key value pair, like in JSON, right? So something like key and value. This is called a claim in the JSON Web Token world. And it's not really specific to JSON Web Tokens. It's just how key value pairs, how do I put that? It's like a general term in the IT security world. So a key value pair or this claim is like an assertion, like a statement about someone or something. And this is like a general term in the IT security world. So that's why it's called claim, because you might ask, yeah, but why don't they just call it key value pair? That's like way easier, right? Yeah, totally true. Would be way easier. So, and the important thing to understand is that these claims, they are, you can have private and public claims. So there's like a couple of predefined claims, for example, EXP, which stands for expires, which is the expiration date until this token is valid, which is just a Unix timestamp, for example. And issuer is like the entity or server or service that created this token. Subject is kind of like the client ID or the one or the entity for which you create like the token for, right? So if I log in and you give me like a token, then I am like the subject, because the token, you give the token to me, so I am like the subject. So that thing, like all that stuff can be like a little bit confusing sometimes, but I think we can get the hang on it. And now that we have covered these kind of these two things here, like the header and the claim set, let's have a look at the signature. So the digital signature is like the last part. It's also officially optional. You can have tokens without signatures, but they are kind of useless, and that's more like a security vulnerability. So you want to avoid you don't want to accept tokens without signature. And the question is now, how do we actually create these signatures? So there's a couple of steps involved. So the first thing is you take your header. So in that case, for example, this one with algorithm and type. You could also use like, I don't know, key ID, like my key ID. And you base64 URL encode this. Now, to be super precise, I just put here, okay, you take the UTF-8 bits like of all of this, and then you base64 URL encode, right? Just to be super clear. But if you want to know like all these details, then I would really encourage you to look up like the details in this RFC. It's RFC 7515. So there you find like all the details if you're interested. Okay, so you base64 encode like the header, and you base64 URL encode. That is important. URL encode, so base64 and base64 URL encoding are slightly different, because base64 URL encoding is URL safe, so you can put it inside of a URL. That's why it's called base64 URL encoding. It's like a small subtle difference. A lot of people just say base64 encoding, but if you're like really strict, that's actually not correct. It has to be base64 URL. Okay, so you base64 URL encode your header, and you do the same thing with the claim set or with the payload. Why is there a new? Okay, let me just remove this. So you do the same with the payload. You take this thing, you base64 URL encoded. And then you end up with this orange thing over here. So it's not super interesting to see this, right? You just have, yeah, it's just base64 URL encoded. And then, and that is the interesting part, you create the signature. And the way you do this is you take your header, so this base64 encoded thing that we just created, you put like a dot, like you concatenate it with a dot, which means you just glue a dot at the end of this string. And then you put the base64 URL encoded claim set as well. And this is basically the content that you are going to use to sign your token. And then you put this content along with your secret. So remember, that was like the key we've always drawn before, inside of your algorithm. And what this is going to do is it's going to produce the actual signature. And the output of this is just going to be like bits or bytes. And I just wanted to get like back real quick. So remember, like when we talked about how to create like a signature, then I said, okay, it depends on the content and it depends on your key or on your secret. So in that case, this green box here, the content, corresponds to the header, the dot, and the claim set, all base64 URL encoded, like separated with a dot. And your secret is basically your private key or like some secret that you have randomly generated before. And this algorithm is then the signature algorithm you use. So for example, HS256 or RS256. And now the important thing to understand is that the raw output of this thing is just bits, like it's zeros and ones or bytes, right? And now the thing is, like, what do you do with it, right? You don't want to send like just a series of zeros and ones over the wire, because you want this thing to be compact. And that is why you typically serialize it into its compact format. So that means if you pass a token around, what you just do is you base64 URL encode just all parts. So we have already done this for the header. So we have base64 URL encoded it. Then we add like a dot as a separator. Then we add this base64 URL encoded claim set, which is basically this part or the exact same part that we have used to create the signature. And afterwards we put the signature. And it's not the raw bits, but like the base64 URL encoded octets or bits of the signature. Okay, and if you ever come across like these things in the wild, you can actually tell by just looking at this thing and looking at how many dots it has. So typically a JSON Web Signature token has like 2 dots, which separates like the header from the claim set and the claim set from the signature, right? So this red thing here would be the base64 URL encoded header. Then you have a dot. Then you have the claim set, which is like the orange thing. Then you have a dot, and then the base64 URL encoded signature. And I just added like new lines so that it's easier to read. But in reality, you would not have like new lines. It would just all be in one line. And by the way, if your token does not have like a signature, then this part here like would just be missing. And then you should not accept it if it doesn't have a signature, which is a very common attack vector for JSON Web Tokens, but this is most of the time disabled. Okay, so that is pretty much how you create signatures. And I now want to go into detail about this algorithm here, right? Because you have previously already seen that there's different types of algorithms. Now we know what content like we use to create like the signatures, but we haven't talked about the different types of algorithms yet. So let's just do that right now. So if you go to the RFC 7519 specification, you will find something like this. Of the signatures and HMAC algorithms, which stands for Message Authentication Code Algorithms, specified in the JSON Web Algorithms, only HMAC SHA-256, also known as HS-256, and none must be implemented by conforming JWT implementations. So that means if you were to write a library, the only algorithm or signature algorithm you have to support are HMAC and SHA-256. We're going to cover in a second like what that is specifically, and none. That is the thing that I've already mentioned previously, that you can have tokens without signatures, and then your algorithm like is just none because you don't have a signature. And here it goes on to say, well, but it's also recommended that you also implement this RSA, SSA, and then a couple of other things with SHA-256, also known as RS-256, and ECDCA, which stands for elliptic curve digital signature, and so on with elliptic curves. So basically, in a nutshell, what this means is you have different types of signature algorithms, one of which is HMAC and SHA-256, also known as HS-256, and you have to implement that. And pretty much all implementations or open source libraries that you will find also have support for RSA and for ECDSA. So RSA and ECDSA comes from the world of public key cryptography, where you have a private and a public key. So we're going to cover that in a second, what the difference is. And they provide kind of similar guarantees like this RS-256 and ES-256, but mathematically speaking, they're different. But you don't need to know all the details. You just need to know on a high level what the major difference between like these public key, private public key types of signatures are and HMAC. And that is what we're going to cover right now. So HMAC is the only algorithm that you, or like the only algorithm you have to support, right? It was HMAC and none. I mean, none doesn't really count as an algorithm. So HMAC is pretty much the only algorithm. And HMAC stands for Keyed Hashed Message Authentication Code. And you don't need to know like specifically how all of this works and with hash functions and all that kind of stuff. The only thing that you need to understand on a conceptual level is if you use HMAC-based JSON Web Signature tokens, or like in general JSON Web Tokens, you need to have a shared secret. So that means if two servers are talking to each other, in order to create a token, you're going to need a specific secret. And in order to verify the token, you are going to need the exact same secret. So you need to share like this secret between the parties. And that is like one way of doing it. So it allows for an easy bidirectional communication, of course, because I mean, you have a shared secret, right? You talk to the other team before you say, hey, let's just use this secret, and that's it, and you're done. So, and computationally speaking, this is also easier and not as expensive as like other algorithms. Okay, so you can just share the secrets. One problem is that if either of these servers like get hacked, then you can basically impersonate server A as well, right? Because since you can create and verify tokens with the secret, like if you use HMAC, if you have the secret, you can do everything. You can both create and verify tokens. So that means if any of these parties get compromised, then it's over, right? So that is like the big downside of like HMAC. And this is very different from RSA. So I think RSA is probably one of the most like known or common public key cryptography algorithm. And what this means is instead of just having one secret, which you have to share, like in case of HMAC, you have to share secrets, you have a key pair. And that means you have a private key and you have a public key. And the private key is much, much more powerful than the public key, because with the private key, you can create tokens and you can verify tokens. But with the public key, you can only verify tokens. And now some of you might say, yeah, but why is this thing called like RSA, SSA? I only know RSA. So RSA, SSA is basically a special version of RSA, which has these exact properties that I just mentioned. So if you have the private keys, you can create signatures and you can verify. But if you only have the public key, then you can only verify. And this actually leads to a very interesting setup, because let's just imagine the following scenario. Okay, I just have to zoom in a bit. I hope you can see everything. Okay, no, I think this one is not visible, right? So let's just pull this a little bit over here. Yeah. Okay, so let's say we have two teams, and these could be two different companies, right? And they want to build like some integration, like some server-to-server communication, for example. So what is typically done is that team A is going to create a key pair. So it's going to create a private key and a public key. And team B is going to do the exact same. They will just have their own private and public key, right? So in the end, we have 4 keys, 2 private keys, right? The ones that are green here, and the public keys, the ones that are red here. And what now happens is that every party gets to keep their private key. So server A or team A has generated the key pair, private key and a public key, and they keep their private key and they keep it secret. They don't exchange it. And the same with server B. So every party keeps their private key. The only thing that is exchanged though are the public keys. So basically team A is going to send the public key over to team B and say, hey, please use this public key, and if we send a request, please use this key to verify like our tokens, and if this works, then we're fine. Then our communication works. And the same the other way around. So team B is going to share their public key with team A, and then you have a setup like this. So server A runs with the private key of team A and with the public key of team B. And this is pretty much the same on the other side. So server B runs with the private key of team B and runs with the public key from team A. So that's kind of a little bit confusing. So basically everyone keeps their private key, right? You keep your private key private and you just exchange public keys. And what this allows you to do now is you can have like a bidirectional communication. And if either of these parties gets hacked, like it's not as bad like with HMAC before, right? Because say if server B gets hacked, then the hacker can impersonate server B because they have the private key, but they cannot impersonate like server A because team A has only shared like the public key, and well, now they have the public key, so they can verify that the message comes from server A, but that's it pretty much. And this is like the main advantage of using like an RSA-based approach, or using like these elliptic curve digital signature approach, right? This other algorithm we've talked about, this one. So this elliptic, this ES256 and this RS256, like they provide similar guarantees, but they're different on a mathematical level. But there you also have like private and public keys. But since RSA is like so common, I just thought, okay, let's just cover RSA. And ES256 is just different on a mathematical level. So the key takeaway here is if you use HMAC, you have a shared secret and you really need to trust like the other party. Whereas if you use like an RSA SSA or RS256 or this other algorithm here, ES256, you have like a key pair and you just exchange the public keys. Now the main downside of basically this approach with RSA is that it's a little bit, or like it's more expensive to do it because in terms of computation, like RSA just has like, you just need to do more calculations. So HMAC is like faster, but most of the time this just doesn't matter at all. Like you just want like good security and you don't want your system to be compromised, because if your system is compromised, then it could have like a really severe impact on your business. You might even close down your business. You'll get sued, like that kind of stuff. So that's why this approach with RSA is like actually pretty common. Yeah, so that's it pretty much for our huge explanation of JSON Web Tokens and JSON Web Signature tokens. Man, can't believe it. It was like 45 minutes. If you stick along so long, then congratulations. Not a lot of people do that. So if we sum up, you can say, okay, there's two different types of JSON Web Tokens. One is signature-based tokens and one is encryption-based tokens. With the signature, you can make sure that if the content is modified, that you detect it. And with the encryption-based token, you can encrypt data. And here with the signature token, the key here to understand is that if you use HMAC, you have a shared secret. If you use RSA or ES256, you have like private and public keys. Yeah, so that's it pretty much for this tutorial right now. So I hope this entire world is kind of a little bit clearer right now. If you have any questions, please write me a comment. Please also give the video a like, and please also subscribe to the channel, because it takes like a lot of work to kind of draw all these diagrams, you know. So as I said, leave me a comment if you have a question. You can also reach out to me on Twitter. My Twitter handle is @productioncoder. And if you're interested in like how all of this works, like how you would actually code all of this and how this works like in practice, then it's now a good time to subscribe to the channel as well, because I'm going to release this server-to-server communication series in which we are going to code this scenario, like, where is it? This scenario down here with both HMAC and RSA based tokens. So I hope to see a couple of you guys around there. Thank you very much for watching, and I hope to see you in the next video.